Welcome to the second in a series of introductory videos on the development of an understanding of atomic structure. In the first video of this series, which is linked below, we saw a historical perspective where over the past 2 millennia, people had developed an understanding that atoms did exist, that different atoms of different elements had different properties, and that atoms were made of smaller particles, specifically protons with a charge of +1, neutrons with a charge of 0, and electrons with a negative charge. Up to this point, nobody was sure exactly what an atom looked like, but they made the assumption that since opposites attracted, it must be a clump of matter with a bunch of pluses, minuses, and zeros all stuck together in the middle, essentially resembling a loaf of raisin bread. While this assumption was logical, as we know now, it was wrong. At the beginning of the 20th century, 4 key experiments were performed that showed what the atom actually looked like and gave insights into what the structure is and the chemistry that was involved. These experiments were performed by Max Planck, Ernest Rutherford, Albert Einstein, and Niels Bohr. Before we get into what the atom looks like, there's a need to get into what people understood about light at the time at the beginning of the 20th century. When we're talking about light, we're talking about all forms of electromagnetic radiation. At the turn of the last century, people knew several things. For example, they knew that all radiation traveled at the speed of light, which is a universal constant of 2.998 times 10 to the 8th meters per second. They had also observed that light had traveled as a wave, which means it had a wavelength, the distance from the height of one wave to the height of the other, and a frequency measured in cycles per second, leading to a relationship where the speed of light being a constant, there was an inverse relationship between wavelength and frequency, so that the speed of light always equaled the wavelength times the frequency. Therefore, if you look at the full electromagnetic spectrum, stretching from radio waves all the way through gamma rays, you can deduce that radio waves, having the longest wavelength, had the lowest frequency, and gamma rays, having the shortest wavelength, had the highest frequency. Max Planck, the first researcher on our list, made the most indirect contribution perhaps to understanding the atom, but he also made one of the most profound contributions to the understanding of the universe at the beginning of the 20th century, and he did this with a rather odd study. Max Planck was interested in things that were called black-body radiators. These were ingenious devices that were essentially the first lasers and were essential for the study of physics. A black-body radiator was essentially a hollow metal sphere that had a pinhole drilled in it. That sphere would be heated up, and when it heated up, it would produce light. However, since it was a quote-unquote perfect black body, there was total internal reflectance, so the light produced internally would just bounce around the inside, and no light would be produced from the surface. As a matter of fact, the only light that escaped would be anything that could get through the pinhole. In order to do that, that light had to have a couple of properties. First of all, the amplitude of the wave had to be low enough so that it could fit through the pinhole to remain in phase. Also, it had to perfectly align with the pinhole. Any waves that did not align with the pinhole would just be reflected. Any waves that went through the pinhole would be reinforced. In this understanding of the time, very common perception, you will note that if you heat anything up, it begins to glow. As you heat it up higher into higher temperatures, it appears that the color changes, going from a red to an orange to a yellow all the way to bright light. The reality of what happens is that the wavelength of the light emitted doesn't change. The wavelength is actually controlled by the size of the pinhole. What does change is the amount of light that goes through. As the heat increases, the amount and the number of photons of light that are transmitted increase, and eventually they overwhelm these receptors in the brain so that the eyes can't distinguish the colors of light anymore and everything looks white. What Max Planck contributed was called curve fitting to the experimental data. Many people had measured the intensity of the light as a function of temperature, and that gave a rather odd-shaped curve, which was not at all symmetric. If you look at the intensity of light versus the temperature, you will note that you have an asymmetric curve that's longer on one end, shorter on the other. The details of what Max Planck found out are shown in this part of the video, and are not essential to know at this stage. The point of curve fitting is that you are mathematically trying to match the exact scientific data. Planck was able to do that with an exponential curve. If you can match what is shown in nature, you can find through the math a greater understanding of it. For example, in Planck's curve fitting, he had two variables, alpha and beta. Over time, he solved for these variables and found out that they depended upon two known constants. Alpha depended on some number h. Beta depended on both h and another number, k. K had been known. K was something called Boltzmann's constant. From an introductory chemistry course, it's rather easy to determine Boltzmann's constant. Boltzmann's constant is essentially the gas constant divided by Avogadro's number. You get 1.38 times 10 to the minus 23rd joules per degree Kelvin. And what this represents is the potential energy of one particle moving through the universe as you increase temperature. The second constant, h, was something brand new. And it was called, in Planck's honor, Planck's constant. It had a value, 6.626 times 10 to the minus 34th joule seconds. But what made it totally unique and new in the understanding of the universe is it had no equivalent in the known science. It was not based on Newton's law of motions or any known wave phenomena. Planck himself was not actually sure what this constant was, but he rather poetically called it the quanta of action of the universe. As you move on in your study of chemistry and physics and the physical world, you will find out that this is indeed true. Planck's constant shows up everywhere. The net result of Planck's work, for our purposes in studying the atom, is that he found out that light has energy, and that energy was proportional to the wavelength, where the energy of a particle of light, or a photon, is Planck's constant times the frequency. When looking at our previous view of light, we had seen that light has a spectrum, from radio waves at long wavelengths and low frequencies to gamma rays at short wavelengths and high frequencies. We now understand, thanks to Planck, why you can listen to the radio on the beach. The beach sun will give you a sunburn, but the radio won't hurt you at all. Since energy is related with frequency, anything at the low frequency end of the spectrum is going to have a low energy. On the other hand, You don't want to take any more X-rays than are necessary because anything at the high frequency end of the spectrum has a high energy. Since the speed of light is known and related, we also know that the energy equal h times the frequency could also be expressed as h times the speed of light over the wavelength. The second key experiment on our list that led to the understanding of the atom was performed by Ernest Rutherford and is the Geiger-Marsden gold foil experiment. While this might seem odd by modern standards, it must be remembered that at the time, people did not know what the atom or what matter itself actually looked like. In this extravagant experiment, alpha particles, high-energy helium nuclei, were accelerated at a sheet of gold. Gold was chosen for a very good reason. It happens to be the most malleable metal, meaning that a small amount of gold can be beaten into an incredibly thin sheet, only several atoms thick. What was expected at the time was referred to as firing a shotgun into a piece of tissue. It was expected that obviously the alpha particle would blast a very large hole in the gold, and then the particles would pass straight through to the other side. What actually happened, however, was slightly different. First of all, the alpha particles did pass through the foil, but instead of passing directly through them, they scattered in several directions. Also, most surprisingly, the foil remained intact. What this experiment showed was that, in fact, matter is mostly empty space. The fact that the alpha particle, which in itself was matter, a helium nucleus, could pass straight through metallic gold indicated that there was plenty of room in between the atoms. Additionally, since the particles scattered instead of passing straight through, it gave an indication that whatever mass was present in the gold had to have had a positive charge, because it was able to repel and change the trajectory of the positively charged helium nucleus. This was, needless to say, quite surprising, and the first clue as to what the atom actually looked like. The next experiment on our list, Albert Einstein, who was famous for his E equals mc squared. However, in this case, he is also famous for something else. The experiment was called discovering the photovoltaic effect. This effect is essentially the same technique used in motion detectors and in department store security devices. Albert Einstein knew, thanks to Max Planck, that light had energy, and that energy was measurable. It had to do with the frequency of the light times Planck's constant. The question was, how can this light then transfer energy? In order to find out, he very simply shone light at a known wavelength on a piece of metal. He found out that by doing this, he produced an electric current in the metal. He knew an electric current had to do with the motion of electrons, and that light was the thing that caused the electrons to move. He also knew classical physics. Newton says an object at rest remains at rest unless acted upon by an outside force. In this experiment, the force provided was the light that was shown. What makes Einstein Einstein, putting two and two together, he came up to the rather shocking conclusion that if force is mass times acceleration, and light provided said force, light itself has to have mass. This experiment was the fundamental proof of what is now known as the dual nature of the universe. Prior to this time, physics had been divided into Newtonian physics, which had to do with masses, velocities, and masses in motion, and also wave dynamics having to do with reflection, refraction, and things like that. In fact, Einstein showed that everything in the universe behaves simultaneously as a particle and as a wave. Additionally, he produced an electric current. An electric current, as mentioned, is moving electrons. If the rather small force imparted by light was enough to move an electron, that means the electrons themselves were never very tightly held by the nucleus to begin with. He was able to measure this and came up with something called a work function, where the energy of the light had to be equal to the energy of the electron. The total energy of the electron could be measured through the current at 1/2 mv squared, plus an unknown amount of energy that was needed to separate it from the nucleus and send it on its way. We now know that this work function is essentially the first ionization energy of any atom. The final key experiment was performed by Niels Bohr. He was taking what is known as the atomic spectra of hydrogen. As you probably know, most things begin to glow when they get heated. He chose hydrogen because it is the simplest element. Every element also gives off a specific color. In hydrogen's case, that color is yellow light. Very simply, Niels Bohr heated up the hydrogen, and what he expected to happen was as follows. Since yellow is a primary color, passing it through a prism should give you no effect whatsoever. Prisms turn white light into the various colors, but primary colors should just be refracted and come out the other side. What actually happened was that the light emitted by the hydrogen was split by the prism into multiple different wavelengths. These wavelengths were very discrete and well separated, unlike a regular spectrum where the colors blend into each other. These wavelengths were widely separated. Bohr knew from Planck and Einstein that energy was related to the frequency of light. Since he observed multiple wavelengths and therefore multiple frequencies, that means that multiple energies were available to the electron on the hydrogen atom. However, this led to an interesting question. He chose hydrogen in the first place because, being the simplest element, one proton and one electron should only give one possible interaction. It shouldn't give 5 or 6 possible interactions. In another leap, Bohr came to the conclusion that that one electron must have various options, that instead of being a set distance from the nucleus, it can be in several different distances from the nucleus, and each of these are well separated. Looking at the planets, he called these distances the orbits of the electron. In the Bohr model, which is called the planetary model, it is shown that the electrons travel in various orbits around the nucleus, and that these orbits are well separated. There are multiple possible orbits rather. So the electron can be either in the first orbit, the second, or the third. With regards to his experiment, he knew that in heating up, he added energy to the system, and then adding energy that would have promoted the electron to rise to a higher energy and a higher orbit. Once that energy was removed, there were many different ways that the electron could get back to where it started from. It can drop from 4 to 3 to 2 to 1. It can drop from 4 to 2 to 1, or it can drop all the way down from 4 to 1. Each one of these different steps and each one of these different pathways is a different distance from the nucleus and is therefore going to be at a different potential energy and give a different wavelength of light. Bohr quantified this, where the energy he observed equal to the light that he observed was equal to a constant, 2.18 times 10 to the minus 18th joules, very simply related by the difference in height that the electron had traveled. 1 over n low squared, the number of the orbit that it landed in, minus 1 over n high squared, the number of the orbit that it started at. This model worked perfectly for predicting every single transition in hydrogen, even several that Bohr was not able to observe. However, it turns out that this model only works for hydrogen and gets progressively worse as the elements get larger. You'll see in further videos, linked in the description below, that Bohr's work did give the starting point to our modern understanding of the atom, and that the relationships that he observed can be